Okay then, so welcome back to the week 4 of the Introduction to the Fluid Mechanics course. Uh, so in this week, in this current week's problem solving session, we will be dealing with problems based on the concepts of forces on a surface immersed in fluid, stability of solid bodies in fluid, and fluid under rigid body motion. So right now again, since only few students have joined, so we will wait for some time and let other students join as well, and then we can start today's session. Okay, so we will wait for 2 minutes, and if no students join, we can go ahead with the session, go ahead with our regular agenda, and then discuss the problems. Okay, so we'll wait for 2 minutes. Okay then, I feel that I guess we can start the session, and other students can join accordingly. So let me just check the mic if it's working. Okay then, it seems it's working, so we can go ahead with the session. Okay, so as I already mentioned, we will be discussing problems regarding primarily these three topics that were discussed in the week 4 of the course by Professor Chakraborty. And to begin with, we will discuss on forces on a surface immersed in fluid. Okay, so as our regular agenda, we will not dive deep into the entire derivation or the entire detailed derivation that is taken by Professor Chakraborty in the lecture. So we will not dive deep to the entire derivation. I'll just go through briefly upon the concepts, try to uh, try to revisit the concepts a bit again, in a just slightly revisit the concepts again, and then once the concepts are clear, basically revision. So once if when the concepts are clear and we have revised it once, we look upon the problems that are based on these topics, and through those problems you will be able to solve the questions that are asked on your current week's assignments. Okay, so to begin with, the concept of center of pressure comes into picture for the first topic that comes into our mind is the center of pressure. So center of pressure is basically the point of application of the buoyant force in the case of a immersed uh, in the case of an immersed body or submerged body. In a case of immersed body, or in the case of a completely immersed body or a partially immersed body. Okay, but in this case, in the current topic, we are primarily concerned in the case of completely immersed bodies. Okay, so we will deal with the stability or dynamics of floating bodies separately and not in detail, but and we are and in the case of floating bodies, we are primarily concerned in the stability of the floating bodies rather than a detailed dynamic analysis of the uh, floating bodies. But in our current course, the force analysis is being primarily done for completely immersed bodies or submerged bodies in a fluid. Okay, so center of pressure basically determines the point of application of the buoyant force in the body. Okay, like since the body is immersed in a fluid, the fluid will act, the pressure, because of the pressure enacted by the fluid on the surface, there will be a force that acts on the surface, and we will assume that I'm sorry, this force acts through a particular point of application. In the case of a body, say in the case of a body in not in a fluid, say if in the open atmosphere, though the atmospheric pressure also plays a role, but since the atmosphere is so lightly so less dense compared to say some fluids such as water, so the effective difference in the pressure distribution because of height is not captured in the case of air. But generally saying, in the case of when the object is placed in a atmosphere in open air, we assume that the entire body mass acts to a particular point of application, that is the center of gravity of the object. So similarly, when the object is immersed in a fluid, because of the pressure distribution of the fluid, and this pressure is itself that acts on the body, we assume that force due to pressure itself acts on a body through a particular point of application, and that particular point of application is the center of pressure. So the expression for the center of pressure is given by this equation, where yp denotes the depth of the center of pressure, yc denotes the depth of the center of gravity, and ic denotes the moment of inertia of the object or the plane in our consideration, and a denotes the area of the plane, and yc denotes the center of gravity of the object. Okay, and by this expression itself, since these terms can never be negative, we can clearly see that yp is always greater than yc. Okay, which basically means that center of pressure lies below the centroid or the center of gravity of the object. And this discrepancy in the center of pressure and center of gravity can be understood by this following example as well as this following diagram. Okay, so consider that there is a rectangular plate immersed in a fluid, okay, which has a height h and width b. Okay, and say the upper edge of the object is placed at a depth of a from the free surface, this inverse triangle and these lines denote the free surface of the liquid. Okay, so since we know from the hydrostatic law that it is dou p by dou z is equal to minus rho g, from the hydrostatic law we know that pressure varies according to the height of the or the depth of the object. Okay, or in a more simplified manner, if there is no accelerating components in other direction, so dp by it essentially becomes dp by dz is equal to minus rho g. Okay, so we see that pressure here varies with the depth of the object. Okay, so it is a linear relation, so it basically means that pressure increases linearly with the depth. Okay, and I'm sorry, yes, it essentially tells us that pressure increases with the depth okay, increases linearly with the depth. Okay, and that's what this distribution shows us. So now if you're going to take a mean about this for this particular distribution, you will get to know that this mean will not be in the center of the object, but rather be somewhere nearer to the lower edge of the object, because the weightage of the pressure distribution is more towards the lower edge of the object, and that's why we see that the center of pressure lies below the center of gravity of the object. Okay, so if we take this example and plug in the values of yc and ic and a in this expression, so we get that the net force that acts on the body, the net pressure force that acts on the body would be given by rho g a hc. Okay, it's a net force, so rho g remains constant. Now we are not particularly now concerned with numerical values, just say we are trying to express the force, the net force and the center of pressure in terms of the given parameters. Okay, so we get that F is equal to, or pressure force, we term it as pressure force. Okay, okay. So this pressure force is equal to rho g b into h, which is the area of the object, and hc is the depth of the center of gravity of the object from the free surface, which would basically be a plus h by 2. Okay, it's very simple. A and half of the length of the object, h by 2. So this is the pressure force. Now we want the point of application of this force. So that is found by this expression. Okay, so which is given by yc plus ic by a by yc. So yc would be a plus h by 2 plus ic for this configuration, and now and we are concerned with the area moment of inertia with respect to the x-axis. Okay, say this is our coordinates, then we are concerned with the x-axis of the object, area moment of inertia with respect to the x-axis, that is basically ixx. Okay, so that will be given by bh cube by 12 divided by area is again bh, and yc is again a plus h by 2, and we will see that since this quantity is positive, so yp is certainly greater than the yp is certainly greater than yc in this case. Okay, and the pressure and the stress tensor for this kind of configuration is given by this. Why, you may ask? Because the only uh, stress that acts on the object is because of normal stress, because of the pressure. Since the fluid is static, since we are primarily dealing with fluid statics right now, so since the fluid is static in this current case, there is no shear in the fluid, so there is no scope of having shear forces in the case of in the current configuration, and that's why there are no shear stresses, and only there are normal stresses that too only because of the pressure of the fluid that acts on the surface. Okay, surface of the object. So now let's take a bit more complicated example. So it's a bit more complicated, and I think this example was done by Professor Chakraborty in the class, but just for the sake of revision, and since revising the concepts and the way of solving problems will help you all and me as well to understand the assignment problems in a better way, so let us discuss this example. Okay, so the current configuration tells that is something like this. There is a say there is a dam. Okay, so there's a dam, so there's a certain wall, and there is a gate that is hooked or is attached to the bottom of the surface through a hinge. Okay, and this gate is of interesting shape, that it is now semicircular. Okay, this does not look like a proper semicircle, I'm sorry for that, but it's actually a semicircle. Okay, and so now we are asked to find this force F. Okay, we are asked to find this force F that would stop the gate from being opened. Okay, so since there is a fluid in this region, and this fluid would exert some pressure force on this gate, okay, that would try to open this gate up. We want to find the value of the force F which is applied on the upper edge of this gate, so that we can stop this gate from being opened. Okay, so that's the question. I hope it is clear. And these are the value of various parameters here. So h is the depth of the water and r is the radius of this particular semicircle, and o is the point mentioning the hinge of the object. Okay, I hope the all the parameters are clear now. And okay, so now and this is the let us do the and let us discuss a free body diagram of the gate that will give us more insight on the problem. Okay, so this is the free body diagram of the gate, and say fp is the point of application of the pressure force. Okay, and as I said, this would be below the center of gravity or the center of the object. Okay, so you can see that this is not directly at the center, but somewhat below the center of the gate. Okay, geometric center, if I may say. And moreover, and this is the force that we need to find. So it acts on the upper edge of the gate, okay. And since these forces are not does not act through the same line of action, so there will be a certain moment generated because of these forces, okay. But we want the value of the force that just stops the gate from opening, nothing more, nothing less, but just stops the gate from opening. So it basically means that the gate will be at equilibrium, okay. The applied force just stops the gate from opening, okay. That's why uh, uh, the gate will be in equilibrium. So the net moment with respect to O, say, would be 0, okay. So that's what we have written here. So the moment because of this force F that we need to find, I will just mark it a question mark here, that would be more helpful. So this force F would be F into R, that would be equal to Fp, this force Fp into Y1. Now what's Y1? So Y1 is again the point of application of the force relative to the bottom surface of the gate, okay. So if you go back to the diagram here again, so so Y1 would be basically this height, okay. This would be Y1. Let me just draw it so that it is not confusing for students. So this is Y1. So Y1 basically would become H minus Yp, okay. So that is shown here. It is H minus Yp, and again Yp is itself is Yc plus Ic by Ayc, okay. Now the interesting thing is we need to find F, okay. So in order to find F, we essentially need the other components to be known. Say we know since we know the configuration of the gate, IC and A are can easily be found, okay. Then if these two quantities are found, then and if we are able to represent Yc in terms of our given parameters, then it basically becomes, this term is known, okay. This is known, but the additional unknown that we have right now is Fp, that we need to find out the value of F, okay. So there are two unknowns right now. But if you recall in the lectures from Professor Chakraborty, he mentioned that Fp cross Y1 is basically the sum of all the moments. If we consider this can basically be considered as sum of all the moments that due to the force that acts throughout the surface of the gate, okay. So this is essentially, it can be considered as an effective point of application of the net force, okay. But essentially what would happen is that since it has a finite length, so there will be certain point of applications of the force, okay. And if we generally consider, there can be infinite number of point of applications, okay. And all these point of application of the pressure force will generate certain moment on the gate, okay. That needs to be balanced. But to simplify our analysis, we assume that the net pressure force, that is Fp, acts to a particular point of application, okay. And moreover we want to find that particular force in terms of our known parameters, that is H and R, okay. Say H and R are the parameters that we need that we present our final solution with, okay. No other parameters, okay. So we want to simplify our analysis, our expressions even further, okay. And that's why in order to do that, what we essentially do is that instead of finding Fp explicitly, we find the net force, the net moment because of the pressure that acts on the surface of the gate, okay. So in order to do that, again we need to perform an integration that takes into account the moment because of all these forces that acts on the gate, okay. So let's take a elemental area. Let me just zoom it in there, okay, then it will be clear. So consider this is our semicircle. I'm extremely sorry that this does not properly look like a semicircle, but it's essentially a semicircle, okay. I'm sorry for the bad drawing, okay. So consider this small displacement as d theta, angular displacement as d theta, that is represented here, and this length would be r, right, this total radius is r, but say this particular element is at a distance of say r, small r, then this arc length is given by r d theta. Okay, and this particular distance is say dr. Okay, so the the elemental area would be essentially be given by r dr d theta. If we consider it essentially to be a square, then it is say r d theta for a very small distance. I know it will not be equal, but say for a very small distance we can assume it to be equal. Then r d theta into r would give the area of this square element, which is given by this. Okay, it's not a square, but I'm just saying essentially if we assume that very small element, this slight change in the arc length can be considered to be negligible, and moreover arc can even also be assumed to be straight, and it's just an assumption. Okay, just a very good assumption if we consider this elemental area to be very very small. Okay, and again in the case of a semicircle, again the centroid of the semicircle is given by 4r by 3 pi. Okay, 4r by 3 pi from the base of the semicircle. Okay, so centroid is at a distance of 4r by 3 pi. Okay, and then okay, let me zoom out a bit. Okay, and then this elemental area say is at a depth of h minus r sin theta. Why? Because since this length is r sorry, and this angle is theta, then the perpendicular height of this element from the base of the semicircle or the bottom surface is r sin theta, right? And that's why this object is at a depth of h minus r sin theta. Okay, so the net pressure force because of the fluid would be given by rho g h minus r sin theta. Okay, this is the pressure force, and again we want to find the net moment of this elemental area, right? We are interested in that. So that would be the net moment would be given by dh, say with respect to o, then df is the net applied force, and r sin theta, that is basically this length, would be the perpendicular length from the length from the origin o, say origin o, or basically it is the perpendicular distance between the point of application and the origin. Okay, the point with respect to which the moment is being measured. Okay, so that will be your perpendicular length. So dh would be df r sin theta. Okay, that is the perpendicular length between the point of application and the point of rotation. Okay, if you consider that, and that's why, and the net moment is given by, so I'm sorry, I forgot to define the force. So df would be given by the pressure force, the pressure, that is rho g h minus r sin theta, and the elemental area r dr d theta. Because f is p into a, then df would be p into dA, and dA is r dr d theta, and p is for this particular elemental area is rho g h minus r sin theta. Okay, so df is given by h minus r sin theta rho g r dr d theta. Okay, and then dh would be given by, just multiply extra r sin theta to this expression to get that dh is equal to h r square sin theta minus r cube sin square theta into rho g d theta dr. Okay, we have just multiplied, since this r will also be multiplied and this r will also be multiplied, so it will be h r square sin theta and r cube sin square theta. Okay, that is what we did here. Okay, I hope it is clear. Okay, and this example has already been discussed by Professor Chakraborty, but still just for proper revision, so that we can apply these concepts very easily then to the given problems, I am just revising it. Okay, so we are essentially now computing this component. Okay, This is the moment because of the external force applied. This is the moment because of the fluid pressure. Okay, so this and that will be basically be given by double integral of the net moment that we computed here. You can just interchange it with dh, say. Then for the first I have just carried forward the integration with respect to r, so that gave us, because it's quite simple, it is just because r is just a quadratic term and cubic term was there, so it is much more simpler to integrate. So I just did the integration with respect to r, so we got that rho g is constant, so rho g is constant, so it comes out. Then you can even written here, no issues. So it is, so this term becomes, if the integration is done with respect to r, then it becomes hr cube by 3 sin theta minus r4 by 4 sin square theta d theta. Okay, the integration with respect to theta is still remaining to be done. Okay, and that will be equal to fr, right, this part. Okay, and then we do the integration with respect to theta as well. The integration of sin theta will give us minus cos theta, and we write sin square theta as 1 minus cos 2 theta by 2. Then do the integration to get that, to get theta minus sin 2 theta by 2. Okay, so I hope it's clear. It's just a simple integration. You can carry on the algebra, or the, I'm not saying the algebra, the calculations yourself. So you can just cross verify. Okay, you can revisit the lectures and see this video as well, and rectify your calculations. Okay, it's nothing that complicated. Okay, and again the limits of theta. Okay, let's discuss the limits of integration. Okay, I think it would be a bit more interesting. So sorry for this to and from motion, but I think it's necessary for the conceptual understanding. So the limit of integration for the radial component, that is r, would basically be from 0 to capital R. Okay, because that is the radius of the semicircle, so it is r. And for the theta component, the angular component, since we need to evaluate the net force on the entire surface, so the entire surface will comprise an angle that varies from 0 to pi or 180. Okay, so the limit of integration for theta would vary from 0 to pi. That is being written here. So the limit of our integration here in this case is from 0 to pi for theta. Okay, if we plug in the values of the limits and do the necessary calculations, so we finally get that f is equal to rho g 2h r cube minus 3 minus r cube pi by 8. Okay, and yes, I guess that's all. You may think that there was a r to the 4 and r cube term, so we just divide r by all the terms to get f. So this one we needed to find. So f is given by rho g 2h r square by 3 minus r cube pi by 8. Okay, so I hope it's clear. So now let us discuss next topic. Again an interesting topic, that is force on curved surfaces. Okay, so again I won't dive deep again, and in the analysis or the approximations that is being taken for the analysis of force on curved surfaces, curved surfaces due to force on curved surfaces due to fluid, that I will not dive deep, but still, say if we consider this example. Okay, this is the free surface of the fluid, and this is the curved surface in our consideration. Okay, this is a curved surface. This is not touching the upper surface. It's slightly below the upper is slightly below the surface, so it is completely immersed. Okay, so if you recall the lectures by Professor Chakraborty, there he clearly mentions that in the case of force due to curved surfaces, we essentially decompose the force into two components, into its horizontal and vertical components. And in the case of horizontal components, it would be the pressure force on the vertical projection of the curved surface. Okay, not the entire surface, but the projected area of this curved surface. Okay, so the net pressure force into the projected area of this curved surface. Okay, so the projected area of this curved surface would be basically be a rectangle. If it will be a rectangle, projected area of this shape. Just forgive my drawing. And in the case of the horizontal component, so in the vertical component will basically be the weight of the fluid that is being held by the curved surface. Okay, so if you look into this diagram, let us just label the different points, that is A, B, C, D. See, so what are the forces that may act in this case? Okay, so the weight of the object would act downwards, right? There will be net horizontal force in this direction, and since the it is not completely immersed, so there will be net it is not complete touching the surface of the fluid, so there will be net horizontal force in this direction as well. Okay, so just and the general convention of our forces is, say, denoted by this. Okay, where Fs denotes the net horizontal component of the force and Fb denotes the net horizontal or vertical component of force on this curved surface. Okay, so once we do the net force balance, we find that Fh is given by minus Fh1 minus Fh2. Okay, it's just a basic force balance, and along the vertical direction we get that the vertical force component is equal to the weight of the object. Okay, oh sorry, weight of the fluid held by the curved surface. Okay, so let us consider this example. Okay, so in this case, a circular cylinder is situated such that the left side of the cylinder, if this is a axis of symmetry, then the left side of the cylinder is completely immersed within the fluid. Okay, and in the right side only half of the cylinder is immersed in the fluid. Okay, and half is above the free surface. Okay, so we are now asked to find the net horizontal and the vertical force that acts on this partially submerged cylinder. Okay, so that would be a correct way to describe this scenario. And so the net vertical force, as we mentioned, is basically the net fluid that is being held by the or supported by the cylinder. Okay, so in the case of this cylinder, and again one more concept, there was one more discussion regarding, I guess, the scenarios where the object is placed in such a way that the curved surface is not holding any fluid inside it, but still there is a net horizontal and vertical component. Okay, so in the case of such scenarios where, see, in this case the cylinder is not holding any fluid inside. Okay, it is the outer surface of the cylinder that is supporting the fluid. Okay, so even essentially ask that since there is no fluid within the cylinder, how can it hold any fluid? Okay, but see, as discussed by Professor Chakraborty in the lectures, in such scenarios the net vertical component is found by assuming the case where the hollow surface in consideration supports the fluid, supports the portion of the fluid that would have been if the cylinder was not hollow. Okay, so basically what I'm trying to say is that I hope I'm able to explain it better in a proper manner. So see, for the left hand side of the cylinder, say this part, okay, this particular curved surface, so The current case is that the fluid outside this semicircular region, say if you consider a 2D analysis, the fluid outside this semicircular region is actually holding the fluid, okay, and there is no fluid inside this semicircular region, okay. So in the case of finding the vertical component of force because of this curved surface or because of this current scenario, what we need to do is that we need to find, instead of finding the fluid that is being supported by this curved surface, because in this case it will be zero because there is no fluid inside the cylinder, we assume that there is a fluid within this curved surface of consideration, and then find the net fluid that would have been held by this curved surface, okay. I hope I am clear, and if there's any doubt, we are most welcome to go back to the lectures once again, but this is essentially the point, okay. So in this case, it would be the fluid that would have been kept supported by this particular semicircular region, okay. So that would be essentially be given by this that will essentially be given by pi r square L, the volume of the fluid within this half cylinder, okay. Pi r square L into divided by 2, okay, to consider the half portion of the cylinder, okay. Similarly, in this part, since there is no fluid above this center line of the cylinder, so the only and also in this case this part does not hold any fluid. It's actually this outer surface that supports the fluid. But again, in this case also we consider that we assume that this particular part of the cylinder, this hollow part of the cylinder, supports the fluid to find the vertical component of the force, okay. And so that would be essentially be 1/4 of the volume of the cylinder, that would be given by pi r square into L by 4. We just sum up these volumes and then multiply and just multiply with rho into g, okay, to get the net force, okay, and that would act in the upward direction, obviously, okay. So and the net horizontal component is again much more simpler to find, because it's just again the projection, it is the projection of the surface that we need to consider. So for this hemispherical region, for this part of the fluid, the projected area would be the rectangle of area L into 2r, right? So the net force would be the pressure into the net pressure into the depth of the centroid of the object, right? So that would be rho f g into 2r into L, that is the area, so the net pressure would be, I'm sorry if I'm a bit confusing, I'm sorry. So the net pressure would be in this, for this particular region, would be say pH1, let me write pH1. pH1 would be rho f g, and h would be r, because that is the position of the centroid of the object, right? This is the centroid, so this would be r, and the area would be 2r into L, that is the projected area. So that the projected area would be the rectangle of with area 2r into L, okay. So say just like pH1, fh1, okay. Similarly, for the other other submerged part, this essentially this part, we just need to consider the pressure would be, again in this case would be, say let me do this color, so pH2 would be rho f g into r by 2, that is the position of the centroid of the object, okay. So the centroid object has nothing to do with the pressure distribution, so it remains constant for all the scenarios. So it is r by 2 from the free surface, okay, that's also essential for the free surface. That's why centroid is at a location of r by 2 from the free surface of this part, okay. So that is r by 2, and net horizontal force would be multiplied by area, so rho f g r by 2, let me just write it properly, r by 2 into area would be r into l, right? So rectangle, the projected area of this semicircular 1 by 4 to the center would be a rectangle of area r into l. Okay, that is basically what we have written here. Okay, so I hope it is clear to this time. So I will just wait for a few minutes uh, just to rest up my throat, I guess, so that you can just suck in that whatever we have discussed till now, and then we'll discuss the remaining two concepts and then go ahead to solve the problems. Okay, so here I will just wait for a few minutes and then you can just discuss. Okay. Okay then. I feel we can resume the session. So the next interesting topic, the next interesting topic for discussion for the current week was the stability of submerged bodies. Okay, so submerged bodies and floating bodies as well. Uh, okay, so by submerged bodies we mean that an object being completely immersed or fully immersed in the fluid. Okay, so and that can be applied equally well for us in open air as well, because in the case of we being an open air, it means that we are completely immersed in the atmosphere. Okay, so the concepts of stability this kind of stability can also be applied in consider the stability of completely immersed bodies can also be applied in for us moving in open air as well. But the concept of floating bodies comes into picture and is a bit different, because now we are dealing with an interface of two fluids with different densities, and one having a density of around 1000 times the other. So the concept of stability of floating bodies becomes a bit different compared to the concept of stability of completely immersed bodies. Okay, so in the case of completely immersed bodies, the primary parameters of analysis becomes the center of gravity and the center of buoyancy. Okay, but in the case of partially immersed bodies or floating bodies, the interesting parameters then becomes the center of gravity and the metacentric height or the metacenter. Okay, so let us discuss first the stability of submerged bodies, so complete submerged bodies. So again, I will not dive deep. So I'll just discuss one of the cases. Say I'll discuss the case of the stable equilibrium. Okay. So consider the object in this form. You can essentially consider this to be, say, a air filled balloon, and this one to be heavy weight, heavy, say, highly concentrated heavy weight that shifts the center of gravity of the object down towards the lower end of the object, and this gas filled balloon shifts the buoyant center, the center of buoyancy of the object, towards the upper edge of the body. Okay, see, you can also imagine that if you are just immersing a, say, a balloon attached, say if you are considering a balloon attached to a stone. So in that configuration, the stone would, the entire center of gravity of the object would be concentrated near the stone, okay, towards the stone or at the stone itself, and the center of buoyancy or the net buoyant force that acts on the balloon because of the presence of the fluid, that is air in this case, would be essentially be at the center of the balloon or towards the balloon. Okay, so we are just considering such kind of a object. So, and that's why this is drawn in this particular fashion, and you can see this is completely immersed in the fluid. Okay, so this is a free surface. So for the first case, and the net buoyant force will be equal to the weight of the object. Okay, that's also important because since it's completely immersed, so from the Archimedes principle, the net buoyant force would be equal to the weight of the object. Okay, and then so in this case, the center of gravity is, say, here G, and the net center of buoyancy is B, and B is above G. Okay, so now let's see what happens when we give a slight push, a slight displacement to this object, a slight rotation to this object. Okay, so if the object is rotated in this particular direction, let me just give it a direction, say this one, and name it as applied moment. Okay, okay, so if we apply a certain moment in this, say, in the clockwise direction, say in this direction, so what would happen is that since the buoyant force always acts in vertically upwards, and the net and the weight of the object acts through the center of gravity and always acts vertically downwards, so these these opposing forces will create a moment. Okay, so these opposing forces will create a moment towards the anti-clockwise direction. Okay, and since here we see that the applied moment was towards the clockwise direction, so there is an essential restoring moment, as we term it, towards the anti-clockwise direction, that will try to stabilize the object back to its original configuration. And that's why such kind of scenarios for a completely immersed bodies where the center of buoyancy is above the center of gravity, we term it as a stable equilibrium, because for a particular displacing moment, the object tries to restore itself back to its original configuration. Okay, similarly, the reverse case would be when the center of gravity of the object is above the center of buoyancy, so that would create an unstable equilibrium. Okay, and I guess that is a good exercise for you to draw the diagram and find the direction of the net moment because of the point of application of the buoyant force as well as center of gravity and the weight of the object through the center of gravity, and then see how the restoring, in which direction the restoring moment, if at all it generates, is created with respect to the applied moment, and see does the generated restoring moment is in along the direction of the application of the moment or against the direction of the application of the moment. So if it's against the direction of the application of the moment, it will essentially act as a restoring moment, so there will be no concept of unstable equilibrium, but if it generates a moment and supports the and along the direction of the applied moment, so it will essentially displace the object even further, creating an unstable equilibrium. Okay, so object will try to displace from its original position, so it will essentially become unstable. Okay, so this unstable equilibrium, so it would be basically be G above B. Okay, or B below G, and finally for B equal to G, the object would be at a neutral equilibrium. Okay, so the next case is the case of stability of floating bodies. Okay, and I feel there was a very detailed analysis of the stability of floating bodies with the concept of metacentric height and all the necessary expressions. I'm not going to derive those. Okay, for the sake of saving time and covering up the concepts, I'm not going to derive those expressions. I will just briefly discuss about the concept of the stability of floating bodies, and also I will not dive deep to the concept of metacentric height, how it generates and what is its application. But let us just try to revise rather than learn here, because learning part was expected to be done through the lectures, and just for the sake of a revision, so that the concepts are you can recapitulate the concepts, we are revising those concepts here. But still, if you have any doubt, you can please revisit the lectures by Professor Chakraborty and then just clarify your doubts. Okay, so just give me a few minutes. Okay, so so in the case of floating bodies or partially submerged bodies, the primary parameters of consideration for the stability of the object are the center of gravity and the metacenter or the metacentric height. Okay, so now you may ask, like, why the center of buoyancy does not come into picture for the case of floating bodies. See, in the case of submerged bodies as well as the floating bodies, say, the center of gravity remains constant. It does not change because the mass of the object remains constant, right? So in both the scenarios, the center of gravity remains the same, but the center of buoyancy is a function of the volume of a displaced fluid. Okay, and in the case of some completely submerged bodies, no matter what is the configuration or the orientation of the object, the net volume of the fluid displaced by the object remains constant because it is already completely immersed in the fluid. Okay, so there is no scope of change in the volume of the fluid displaced by the object. But in the case of floating bodies, the volume of the fluid that is being displaced by the object can change or essentially reorient itself according to the orientation of the object. Okay, so similarly, if we consider that, so when the object is shifted or slightly tilted or oriented in a different direction, the center of buoyancy of the object also changes accordingly in the case of the floating bodies. Okay, so if we consider this example, say this is the object, say so this is the object here. Okay, oh, I'm sorry, this is the object placed here, it is floating. So you can see this, most of the surface of the body is below the water, but certain part of it is above the water, so it can still be considered as floating bodies. Okay, so in this case, let us consider a case where here G denotes the center of gravity, so the weight of the object will act through the center of gravity, and say let me just draw it here, okay, that would be better. Say initially, it's not a good color. Initially the center of gravity was here, sorry, and the center of buoyancy was here, okay. Say B bar, okay, not to confuse with this B here. So B bar denotes the center of buoyancy, okay. So let me just draw it. So different color. So this is FB and this is W. Okay. So what happens is that if we now tilt the object by applying a certain moment in this direction, if we tilt the object, say, so what happens is that in this part of the fluid, in this part of the region, lesser fluid is displaced, okay. So since the object goes moves up, so the volume of the fluid displaced by this part of the fluid is decreased, and accordingly this part of the object displaces more fluid, okay. Even if the net volume of the fluid is displaced by the object is constant, say because of this particular angular displacement, it may also happen that the volume of the fluid displaced by the object may increase if the object is pushed downwards even further. So the volume of the fluid displaced by the object would increase. But say there's a scenario where the object is just given an angular or disorientation that results in the lowering of the object within the fluid in a certain in a particular plane, and coming out of the object from the water, particular volume of the object to come out of the water in a different plane, okay. So it may happen that the volume of the fluid displaced by the object may remain essentially constant, but since the orientation of the or distribution of the volume of the fluid displaced by the object has changed, then the center of buoyancy of the object will also change accordingly, okay, in order to take into account this particular disorientation, okay. And that's why in this scenario, even if the center of gravity has remained constant, the center of buoyancy has shifted from its initial position to this particular place, okay. And now the point of application of the buoyant force would act to this new position B, say, and the center of gravity would act along the mass of the object would act along the center of gravity as usual, okay. And now you see, if this was the applied moment, right, you can clearly see again that since there are two forces that acts on the object, and again they are separated by a certain distance, say let me just denote it with different color, say dx, then there is a net moment generated because of these two forces, okay, the weight and the buoyant force. And this moment is again, as you can see, in a direction opposite to the direction of the applied moment, and that's why it essentially acts as a restoring moment, similar to the previous case of the submerged bodies, and tries to restore the object back to its original position, okay. And now if you try to correlate these concepts, you can understand that this stability that we're discussing, especially in the case of floating bodies, essentially comes into picture in a most common example would be the ship, okay. And this ship, because of the waves that are generated in the oceans, can have a certain tilt in a particular direction because of the movement of the waves, okay. Since you know these oceans are not silent, they can become very violent and can create waves that of waves having an amplitude of several meters. Okay, and these waves, this oscillation of these waves could tilt the ship in the left or right direction according to the, depending on the amplitude of these waves. And an essential requirement for the safety of all the crew members in the ships would be that this tilt in this tilt that is being given to the ship because of these additional waves should not uh, what to say, should not make the ship uh, fall down. Okay, this should not make the ship topple. That would be the proper word, I guess. Topple. Rather, it should get back to its initial position that is vertical. This is being vertically straight. So it should try to restore back to its original position. Okay. So that would be the essential feature, safety feature in the case of ships, and that's why the engineers, they design the ships in a manner, in such a manner that the metacentric height is always above the center of gravity of the object. Okay, and like as much as possible, so that no matter uh, how large the applied displacing moment is, the since the metacentric height would essentially be above the center of gravity, it would try to restore the ship to its initial position. Okay, so that's a very important design factor in the case of ships. Oh, I'm sorry. So yes, so there's a very interesting design factor in the case of ships, and that's where the concept of metacentric height comes becomes very important. Okay, so that's one of the applications. So I guess Professor Chakraborty might have discussed some of those examples related to the stability of ships or some other configurations, but this is where the concept of metacentric height becomes very important. Okay, so that's what we are discussing. So in the case of floating bodies, the stability criteria is given by this: that the metacentric height, when it's above the metacenter is above g, the floating body is considered to be stable. If the metacenter is below g, it becomes unstable. And in the case where the metacenter coincides with the center of gravity, it becomes a neutral equilibrium. Okay, so from this you can clearly see that m essentially plays a role, the metacenter essentially plays the role of the center of buoyancy, but it is not exactly the center of buoyancy, because this metacenter is though it is dependent on the center of buoyancy, but it's not exactly the center of buoyancy, because you can see in this diagram it's actually it's actually the point of intersection of the uh, central axis of the body and the point of application of the buoyant force. Okay, so like if this is the axis of the body and this is the point of application of the buoyant force that is being generated because of the shift of the center of buoyancy. So when these two lines intersect, that point is known as the metacenter, and this distance between the center of gravity and the metacenter is known as the metacentric height. Okay, so I hope this was clear. So now we will finally discuss the last topic for this week's session, that is the fluid under rigid body motion. Okay, so again I will just request you to give me a few minutes break, and I hope you are able to, and I will give you some time to suck in all the concepts that we discussed today, and then we will again finish this final concept and then dive straight to the numerical problems and then end the session. Okay, so that's the remaining agenda for today's session. Okay, then. Okay, so just give me a few minutes. I'll be back and revise the concept that we discussed till now, and then we can discuss the final topic for today's session, and then dive to the problems. Okay, so yeah. Okay, then I guess we can discuss the final topic for today's session. And I'm sorry for the delay, but okay. So the final topic of discussion is for today's week is fluid under rigid body motion. Okay, and again, as per our regular agenda, I will not dive deep to the entire details of the derivations. I will slightly discuss the topic, try to capture the governing equations if I can, and then if you have any doubt you can ask, but that's all we can do. Okay then. So as discussed by Professor Chakraborty in the lectures, fluid under rigid body motion. So in this case, this is actually a very approximate analysis of the actual phenomenon, because in this case we assume that the upper layer or upper surface, the free surface of the fluid remains flat, and that essentially lets us to take the approximation that the pressure at that particular interface between the air and the water is constant, and thus we take that at the free surface we take that dp is equal to 0. But since we know that it's not the general, it cannot be it cannot be the real scenario, because we see that when the fluid is being carried, say, by a water tanker, the upper surface of the fluid essentially has a lot of oscillations, right? A lot of oscillations, and that as Professor Chakraborty termed that phenomenon as sloshing. So that is essentially there. But still, even if it's not an exact analysis of the real natural phenomenon, this particular approximation of considering the surface to be flat gives us a very good insight to the behavior of the fluids under rigid body motion. Okay, so let us consider this particular diagram. I hope it is clear. So this is basically a say a container holding particular level of fluid moving on a free surface, okay, with some certain acceleration, say ax. Okay, and because of this acceleration, okay, because of this motion, the surface of the fluid tilts accordingly, like whatever may be the direction of the or the direction of the acceleration, the surface of the fluid would orient itself accordingly. Okay, But the key thing is that since the upper surface of the fluid is flat in our particular assumption, the net pressure change on that particular free surface would be zero. Okay, because there is no, and we know that the pressure varies according to height, and since there is no variation in the surface of the free surface of the liquid, we say that dp is equal to 0. The net change in pressure at that particular surface, or essentially the interface of the air and liquid, is 0. Okay, and now if we write this expression in terms, this complete derivative in terms of the partial derivatives, we can write dp is equal to dou p by dou x dx plus dou p by dou y dy, that is equal to 0. Okay, and again we take the help of, let me zoom out a bit. Okay, so we take the help of our governing equations for uh, fluid motion, where we are not considering the viscous term. So these are basically the Euler's equation of motion. So uh, so and and this equation we consider because there is no shear force in the fluid, because the fluid is not in motion, right? And that's why essentially, since there is no shear force, there is no fluid motion, so there's no scope of having shear forces, because if you when we discuss the dynamics of the fluid motion, we will see that it is the uh, velocity gradients that expresses itself as the shear force in the case of fluid motion, right? And that again is correlated by the Newton's law of viscosity, right? That tau is equal to mu dou u by dou y plus dou dou v by dou x. Okay, this expression. But since all these velocity terms are 0 in the case of this current example, that's why there is no scope of having considering the viscous terms, even if the fluid has a viscosity, right? But since the velocity gradients are itself 0, the viscous term itself becomes 0. Okay, so considering the Euler's equation of motion, we will have dou p by dou x plus rho bx is equal to rho ax. Okay, again along the x direction, since the net body force along the x direction is 0, the expression along the x direction becomes dou p by dou x is equal to rho ax. Okay, similarly along the y direction, dou p by dou y plus rho by is equal to rho ay. And since the net acceleration along the y direction is 0, because we are only considering acceleration along the x direction, we have dou p by dou y is equal to rho g. If we consider by as minus g, then we have dou p by dou y minus dou p by dou y is equal to rho g. Okay, basically the hydrostatic law. But pressure is a partial derivative, because pressure is a function of it's function of x also. Okay, and if we plug in the values of dou p by dou x and dou p by dou y in this expression, we get that dy by dx is equal to minus ax by g. Okay, this is basically the slope of this slope of the upper surface or the free surface of the fluid. Okay, and you can see that since it is minus ax by g, so it will essentially tell us that it is a negative slope. Okay, that is having a slope of this particular shape. And then since as discussed by Professor Chakraborty, since this angle, if we consider, this would be a obtuse angle, so tan theta would actually be a negative of this value, so tan theta would be equal to ax by g. Okay, there is a mathematical origin of this relation, so I suggest that you go back and discuss it. Basically, how the angle varies in different quadrants. So 10 pi minus x would be minus 10x, so that type of expressions. So I suggest that you look that to the expression, so that you can understand why we have discussed that we have how 10 theta become ax by g. But I insist that you go through those expressions. Okay, then again if we go back to the diagram, again sorry for this to and fro motion, the screen is limited and the content is too large to fit in a particular in this particular screen, so I have to go to and fro, but I hope you can understand. Okay, so we got that tan theta is equal to ax by g. Okay, again if we consider that this displacement is to the center line, okay, we consider this displacement to be with respect to the center line of the free surface or the initial free surface. Okay, then if we consider this angle to be theta, right, then this, let me just draw it, that would be much better. Okay, so if we consider the displacement to have this form, then let me use different color. So if we consider this triangle now, and this angle is theta, and we consider that this length is L by 2, sorry, B by 2. Okay, if we consider the displacement with respect to the center line of the free surface, just ignore drawing for right now and assume that this displacement was from the center line of the free surface, then this tan theta will be given by if this displacement is say delta h by b by 2. Okay, and that is what I have essentially written there. Delta h by b by 2 would be equal to tan theta would be equal to ax by g, and that's why from that we will get delta h is equal to axg into b by 2. Okay, so again there was a concept of water spilling out of the tank. So that essentially was discovered by Prof. Chakraborty, that if this delta h, the sum of h naught plus delta h becomes greater than the net total height of the container, so the water will spill out. Okay, so that was the concept, and moreover even after the water spills out, the net relation that we have, that tan theta is equal to ax by g, would still remain to be valid. Okay, so that was discussed by Professor Chakraborty. I insist that if you have any doubt, you can please go back to the lectures and once again. Okay, so the final topic of discussion was the variant of this particular scenario, that rather than moving in a straight surface, assume that the container that contains the fluid is moving in a particular slope, in a sloped surface, in a slope surface. So it will again result in the decomposition of this acceleration components, right? So we would basically get a decomposition of the acceleration components. But now to simplify our analysis, we choose the coordinate axis to be our coordinate axis to be along this sloped surface. Okay, so this would be the x direction, x coordinate, and this will be the y coordinate. Okay, so in this case again the net acceleration of the container, okay, would be along the would only be along the x direction. But since we know that the mass of the object always acts vertically downwards, so this slope would essentially create two different components of the body force that we essentially get here. Okay, so from the Euler's equation of motion, we will again get dou p by dou x minus dou p by dou x plus rho g sine alpha, this is basically this component, is equal to rho a. Okay, so we simplify this expression here, and then for the y direction we get minus dou p by dou y minus rho g cos alpha is equal to 0, because according to our chosen coordinate axis, the net acceleration along the y direction is 0. So the dou p by dou y will be given by minus rho g cos alpha. Okay, so once again we substitute the value of dou p by dou x and dou p by dou y in our complete differential, this in this expression, to finally get that dou y by dou x, dy by dx is equal to g sine alpha minus alpha divided by g cos alpha. Okay, just do the required algebra to obtain this expression. Okay, and now as discussed by Professor Chakraborty, now we cannot essentially say what the slope of the upper surface would look like, the free surface would look like. Okay, it would depend on whether this expression it will depend on the sign of this numerator. Okay, because this will essentially always be positive, at least for the current slope this would be positive, so it will essentially depend on this expression, the numerator. Okay, so if g sine alpha is greater than a, the numerator will become positive, so our slope will be positive, right? So it will be of this particular configuration. And if g sine alpha is less than a, our numerator will become negative and the slope will be of this configuration. Okay, so I hope I was able to clear the concepts that we discussed, that were discussed in the course this week. So if you have any doubt, I again insist that you go back to the lectures, or at least if you have any doubt, go back to the particular sections of the lecture so that you can clarify your doubt and then try to solve the assignment problems. Okay. So as per our agenda, we will try to solve some problems related to the topics, to the discussion, to the topics that we have discussed today, so that it can help you to understand the questions and solve the problems of this week. Okay, or the assignment for this week. Okay. Oh, okay then. Let us see the questions. So this is the first question. Okay, and since unfortunately there are very few students and I have to dictate the question, I will give you some time to see the question, and I have drawn the diagram and all the questions myself, so there's not much issue. But still, let me just dictate the question and give you the answer so that you can just play back the video to and fro to watch the questions and then see the solution. Okay, that would be better. Okay, then I will try to wrap it up as soon as possible, so that since the students have left the session, so I guess it is better that I just wrap up the sessions as soon as possible. Okay, so this is the first question. Okay, a plane gate, these are the key terms. Okay, a plane gate of uniform thickness holds back a depth of water as shown. Find the minimum weight needed to keep the gate closed. Okay, so this gate, this is the current configuration of the gate, and the question is asked that what should be the weight of this gate so that it can keep this water from flowing out. Okay, since if the water pressure is much more higher than the weight of this object, it will try to lift up the gate and the water will flow out. Okay, so we need to know the weight of the object that holds the water in its particular within the container. Okay, so again, this is a straight application of the concept of forces on submerged bodies. So we need to find the first of all we need to find the we need to find the weight of the gate that holds this volume of water in the container. Okay, so let's directly go back to the we'll basically do a moment balance, but let us see the solution. Okay, so if we consider this to be our axis, say O, let me even label it here. So the net moment in the case of an equilibrium with respect to O would be 0. Okay, so the first moment would be because of the two forces that act on this gate are the weight of the object first. The weight of the object that acts from the center of gravity of the object of the gate in this case, and second would be the net pressure force that acts along the center of pressure of this gate. Okay, but as we again know, for some certain kind of problems, it is very difficult to explicitly find the expression for the center of the force that I'm sorry, let me just write it. Okay, so we have that F into yp would be equal to W L by 2 cos theta. Okay, so and if you consider yp, say yp is here. Okay, and this is the, so it would be again be yp, oh no, it is wrong again, so let me write it in such a way that say F into yp cos theta. Okay, so this will be the expression cos theta and again this will also be okay. But again, the thing is that
this force, it's sometimes difficult to find the expression for this force itself. Okay, so rather than doing this multiplication, we try to do the integration to find the net to find the net pressure force because of the pressure distribution on the entire surface of the gate. Okay, so we take the help of integration to find the net pressure force that acts on the surface of the gate. Okay, so just sorry, I'm just curious, just forgive me for the delay. So so it is not that simple, so it would be actually be f uh, v. If I'm just trying to dissociate the force component, say if I'm writing it in terms of, so this will also be theta, right? So sorry, uh, sorry for the delay. So just let us just, this is with theta. Okay, so it would be f v yp cos theta, cos square theta, plus f h, not fb, let me just write, and then cos theta is not needed, so fv is not needed, so you can just write say f. So okay, bear with me. Okay, I'm just trying to show you the simplicity of doing integration, why it is so it is fyp cos square theta plus fyp sin theta cos theta. Okay, if I'm not wrong, so f yp along would act along this direction, and the perpendicular distance would be r yp sin theta. So yeah, this is the expression. Okay, so it basically gives us that only. So never mind. So you can clearly see that for this case again we don't know the expression for f. Okay, we don't know the expression for f, and that's why we need to take the aid of integration to find the net to find the contribution of net pressure force on the gate, and then balance it with the moment because of the weight of the gate, and then find the expression for w. Okay, similar something that similar to something that we did just few minutes before in the class. Okay, so to do that we see that we can go to this equation here, that summation of net moment with respect to O would be 0, then WL by 2 cos theta would be equal to integration of y into df. Okay, so and say y is the distance from the origin O. Okay, Then df is pda. Okay, df is pressure into that particular elemental area, say that would be equal to rho g y sin theta. Okay, so it is, let me just write it here so it is not confusing. So if I use, so if this is the elemental area, say, okay, so df would be equal to rho g y sin theta. Okay, p would be rho g y sin theta, and then from this expression we get that w is equal to 2 by L cos theta into y p dA. Okay, then y into p is rho g y sin theta, and area would be w into dy. If w is the width of the gate, then area would be w dy. Okay, let me just write it for simplicity. So this is a, this is p. Okay, dA. Okay, so again just simplify this expression again. Since theta remains constant throughout the expression, if the gate is in equilibrium, then we can take theta out, sin theta out of the expression to get this expression, and then within the integration we will have only y square by y square into dy. Okay, and the limits of the integration will again be from 0 to L. Okay, well, we need to do the integration for the entire length of the gate. So doing the integration, we get that w would be equal to 2 rho gw. Here w is different, it is the width of the gate, tan theta by L into L cube by 3. So if we simplify the expression further, we get that w is equal to 2 by 3 rho g w small w tan theta L square. Now just substitute the value of all the known values, or all the known terms in this expression to get that w is equal to 68 kilonewton. Okay, so the correct answer in this case would be D. Okay, so now consider next question. A tainter gate is used to control the water flow from a Uniontown dam on Ohio River is shown. The width of the gate is 35 meter. Okay, it is the density of water is 1000 kg per meter cube, and acceleration due to gravity is 9.81 meter per second square. Okay, so this is a diagram. The radius of the gate, curvature of the gate is given by r equal to 20 meter, and depth of water is 10 meter. Okay, so the given question is, so let us take two questions at once. Determine the horizontal force of water acting on the gate, determine the vertical force of water acting on the gate, and the final question is determine the line of action of the force from the water on the gate. Okay, so let us consider these three questions all together and then try to solve the problem. Okay, so this is the diagram that is into consideration for question number 2 to 4. Okay, so so we resolve the hydrostatic force that acts on the gate into the horizontal and the vertical components. So the horizontal component is given by, say, if there is an elemental area shown by this, then the horizontal force that acts on this elemental area is dfh. Okay, so that is given by df. If df is the force that acts, net force that acts on this elemental area, so the horizontal component of force is df cos theta. Okay, and df is given by p into da. So we know p is again given by rho g h. So h is again r sin theta. Right? If r is the radius, then if theta is the angle, then at this point the depth would be depth of this element would be r sin theta. Right? This is the angle theta. Then depth would be r sin theta. Okay, so we write pressure is rho g h, so rho g r sin theta into w is the width of the gate. This is basically, we want to find the dA area, so it is w, it is width of the gate, into r d theta. Okay, it is the length of this elemental surface. Okay, and it is multiplied by cos theta. So dfh is given by rho g r sin theta w r d theta cos theta. Okay, So to find the net horizontal force, we just need to integrate this expression from 0 to theta. Okay, the only unknown here is theta, and we carry on the integration from 0 to theta 1, and theta 1 is found by finding the from the ratios of this length. Okay, the ratio of the radius of the dam, of the curved surface, and the depth of the water. So since the hypotenuse and the perpendicular height is known, so we know that sine theta is the perpendicular height by the hypotenuse, so we can get theta 1 as sine inverse 10 by 20, which is 30 degrees. Okay, so our integration will be from 0 to 30 degree. Okay, so we get that fh is equal to rho g r cube omega sin theta cos theta into d theta. Then we do the necessary integration to find that fh is equal to rho g r square w by 8. Now since all the value of all these terms are known, we substitute the value of these known terms in this expression to get it fh is equal to 1.72 into 10 to the power 7 Newton. Okay, so the integration part, again, I don't think it is a right platform to carry on the integration terms by term, but all the necessary steps are already shown here. So if you have any doubt, you can just ask. But and if there's any doubt in the fundamental understanding, you can just go back to the lectures, revise the lectures to clear your doubts. Okay, so next question was to find the vertical component. Similarly, the vertical component will be given by, since fh is df cos theta, then vertical component will be df sin theta, right? Similar expression, so we write it as similarly df is equal to df sin theta, which will be pdA into sin theta. And again we found that p was rho g into r sin theta, and again there's one more sin theta, so the sin, it becomes sin theta square, and area was omega r d theta, so r, again the r also becomes square here. Okay, so we get dfb is equal to rho g r square w 1 minus cos 2 theta by 2. Okay, we just wrote sin square theta in terms of cos sin square theta as 1 minus cos 2 theta by 2. Okay, so again the limit of integration would remain the same, that would be from 0 to 30 degree. So we carry on the integration of this expression to get that fb is equal to rho g r square w into pi by 12 minus root 3 by 8. And we just substitute the value of known values in this expression to get that fb is equal to 6.2 into 10 to the power 6 Newton. Okay, and the third question was to find the line of application of this force. So we know that if the two horizontal and vertical forces are given here, say fh and fb, and say this is the angle theta, the resultant of the force, then we know that the resultant of the force, angle of the resultant of the force, these two forces, is given by fv by fh. Okay, so tan alpha, if alpha is the line of, if alpha is the angle of the resultant of the force because of fh and fb, so we get that tan alpha is equal to fv by fh. Then alpha will be given by tan inverse f by fv by fh to get, so that we get alpha is equal to 19.8 degree, and which is taken from the free surface of the fluid. Okay, that is basically the line of force passes through the pivot at an angle of alpha to the horizontal. Alpha is equal to 19.8 degree. Let me just write it for removing any kind of confusion. Alpha is equal to 19.8 degree to the horizontal. Okay, so I hope it is clear. So let's check the next question. So next question I would say is very simple. It is just a conceptual question. So I would answer it right away. So the question is regarding the stability of floating submerged bodies. So let's read the question. Here, answer the following questions related to stability of submerged bodies. Okay, we just discussed it very thoroughly. Here, B denotes the distance of the center of buoyancy from the free surface. G denotes the distance of the center of gravity from the free surface. Which among the following conditions ensures stable equilibrium? So that would be the first expression, that is center of buoyancy is above the center of gravity. So basically it would be B is less than G. Okay, since we are considering distance from the free surface, so B should be less than G. Basically G should lie below the center of buoyancy. Okay, then it is for unstable equilibrium, it's just the inverse case. So B should be greater than G for unstable equilibrium. Okay. Just few minutes. Okay. So I will just write the shorter diagram here. So this is the free surface and this is the object, say. Then if this is B and this is G, it is told that B denotes the distance of center of buoyancy from the free surface and G denotes the distance of center of gravity from the free surface. Yes. Then for stable equilibrium, B should be above G, right? So essentially B should be less than G. Okay. B should be less than G, and for unstable equilibrium B is greater than G. Okay. And for neutral equilibrium B would be equal to G. Okay. So that's the solution. Then question number 8 to 9, again this is the diagram. So again this I guess this is related to rigid body motion. Okay. So okay. So the question is, a tank of water is shown in figure 12 in the figure, which is 12 centimeter wide into the paper. Okay, so depth is given by 12 centimeter. The tank is accelerating to the right in the rigid body motion at 6 meter per second square. Density of water is 1000 kg per meter cube and acceleration due to gravity is 9.81 meter per second square. Compute the depth of water on side AB. Okay, I guess again it's a very simple question. We need to find delta H to find the depth of water on the side AB. Okay, since the acceleration is towards this direction, so fluid will displace this particular manner. So we need to find this additional height delta H. Okay, and again we need to find the pressure at the panel AB because of this displacement. Okay, so this is the question. So let's see the solution. So this is a diagram, and from that from again we apply the concept of rigid body motion. First we find the angle theta to obtain this displacement, because we know that delta H by B by 2 is equal to AX by G, right? So from that expression we get that theta is equal to tan theta is equal to AX by G, which is 6 by 9.81, which is 0.612. Okay, so we get theta is equal to 31.45 degree. Okay, so this additional height delta Z, see, say if this is equal to L by 2, say this angle will be theta itself, then delta Z would be equal to L by 2 tan theta, right? You can use this expression as well, there is no issue in that. So delta Z is equal to ax by g is equal to tan theta, right? So you can use any of this expression. You could have found out from this as well, but let us just use. You can also find out delta z from this expression as well. So delta z, sorry, to be equal to L by 2 tan theta. Okay. So we get that delta z would be equal to L by 2 would be 12. So tan 31.45 to get delta z is equal to 7.34 centimeter. And then since we know that this additional height would be basically be h naught, it is in the current case is 9 plus delta z, so h naught plus let me just write it like this. Net height would be equal to h naught plus delta z is 9.9 plus 7.34, it is 16.34 centimeter. So the correct answer in that case would be 16.3 centimeter is shown here. Okay, and we need to find the net water pressure force on the panel AB. Okay, this question is a bit interesting. So we know that in the case of rigid body motion, pressure is function of both x and y. Okay, so we had the expressions dou p by dou x is equal to rho ax and is equal to rho g, right? But it is said that we need to find the pressure distribution on the panel AB. Okay, so x in that case is constant. Okay, so for a particular x, this expression would become dou p by why? Because x is constant. We are asked to find the pressure only on the panel AB. Okay, so the x location for the pressure distribution is kept constant. That's why pressure becomes only a function of y in that for the pressure distribution on that particular panel AB. Okay, and that's why the water pressure on AB varies linearly due to gravity because of this expression. Okay, so we get that F water pressure force at AB would be pressure at AB into the area of the panel. Okay, and that is not, then that is the displaced height of the fluid. Okay, not the initial height of the fluid. Okay, that's why the pressure is given by 9.81 into it is G, here it is G, rho and H. Okay, and area, and this is the area. So we get the net pressure force is equal to 15.6 Newton. Okay.